Hello 108 students, Mr. McCue back here. Hey, we're going to finish up section 10.3. We're on our last page of our class notes. And here for page 6, we're going to kind of wrap up and summarize. And I get a little excited about taking mathematics now to the point where we're going to go back and study and see what we put together and really try to grasp this concept of a function and its inverse function here based on the exponential function f of x equals 2 base 2 raised to the x. Notice here in my notes this was from section 10.2 example 1, so you can go back and reference it. And we're going to graph that, and then we're going to look at its inverse function, and we're going to realize that's going to be a logarithmic function. And so we're going to make this discovery that an exponent and a logarithmic functions are inverses of each other. And we're going to just work on the example that we just did. We're going to prove that it's going to be from page 5, example 3. It's again from our section 10.3 we're working on. Okay, so let's break this down a little bit here. This is where you want to study and observe, and one of the key points we're going to prove to you guys is that once you have a function and a one-to-one function, you were able to swap the x and y coordinates to get to the inverse function. Okay, so with that said, I'm not going to go through all the nitty-gritty details, but I want to graph f of x equals 2 to the x, and again you can reference 10.2 example 1. And what you're going to notice is you're always going to find that elbow point, so you'd start with that. I'd come down here maybe for -2, find the corresponding y value, and as I come up here I might find 2, 4 was on the graph, and maybe finally come up here and realize 3, 8 was also on there. This would be 2. This is -2, 1/4, by the way. Okay, so again, the x-axis is your asymptote for this graph. I'm not going to do it all the way across, but the exponential function will never cross the x-axis. And then let's go through the process of saying we know this is a function because we've done the vertical line test. We know it's a one-to-one because we've done the horizontal before. And we're going to start the process of taking y equals 2x and swap y for x and x for y. And that's what I've done right here. Okay, so look over here. Y became x, x became y. Swap the x and y functions. Now I want to isolate the y, and we came up with the whole concept of logarithm. So I take the exponent, I drop it down, and now I use the word log, base 2, result x. Okay, and we've covered plenty of examples of how you convert that. Now what we got to do is we now have a mechanism to isolate that y, which was the exponent, and we can replace it with our f -1 or inverse function of x, and it's now log base 2 result x. Okay, now that turns out to be, like I've just said, the previous example on page 10.3. We're going through the graphing of it, and you can go back and reference the some of the points there. Remember 1, 0 was found. Might come down here and remember 1/4, -2 was right here. 1/4, -2, and we come up here from our graphs. We found 2, 1. You can see I've highlighted some of these points. Again, go back and study the y-x table expanded, and then the big conclusion here for this proof is we keep making the statement that you can swap the x and y coordinates when you've got one-to-one functions. And so we're going to go here and look at this order pair, which was 3, 8. I didn't happen to do this one, but I'll put it up here, 3, 8. Go over here and say if I swap it and write 8, 3, I'm swapping the xy, yx, and say does that actually hit 8, 3 on our graph? And lo and behold it does, which we've already graphed. So we're starting to prove the concept of our swapping x and y coordinates. Now that you understand this and we believe it, you can use that as a shortcut. 2, 4 became 4, 2. I swapped them. 1, 2, 2, 1. Look at 0, 1, 1, 0, the elbow points. You can come down here and look at these and see that you've got the swapping. And what I kind of find interesting is the symmetrical here, symmetrical aspects of it. This is just me, but it kind of reminds me of butterfly wings. Okay, just kind of, I don't know, they just look like butterfly wings to me. And they look like they could be reflective off of each other, off of a line of symmetry or axis of symmetry. And it looks like if I was going to go right down the middle of them, find the distance between all these points, I would go right down this axis of symmetry, and a little more careful observation, we make a conclusion that the axis of symmetry is y equals x. Okay, if I turn around here, graph these, that means y equals x. For every value of x your input, the output is the same. 2, 2, an example of that. 4, 4 hits it. 6, 6. And you can come down here and say -2, -2 is on it, and that's the line of symmetry. Okay, so with that concept here, we're going to move down to the second half of the page. Again, that's a lot of observations and studies, but that's what we're dealing with. We're now starting in a new aspect of mathematics, one-to-one functions and what they look like when you graph them. Our last thing we're going to work on here to wrap up this section is example 5. We've got a couple application problems dealing with barometric pressure. This is example 5 out of the book. They are going to give you the function f of x equals 27 plus 1.105 log base 10 quantity x plus 1. And all you're going to do is they're going to ask you at 9 miles, what is the barometric pressure? You're going to find f of 9. Simply substitute 9 in. For x, you're going to come all the way over, put it in. And remember the function was x plus 1, so that turns out to be 10. Log base 10 result 10. Oh, that was a special property that when you have the same base and the same result, you replace it with 1, and that's what I did right here. Replace that there. Now that you've done that, it's an exercise now of multiplying 1.105 times itself, times 1, adding it to 27, and you get your answer of 28.105. Okay, so these problems are fairly straightforward. They're taking advantage of some properties here. They say, oh, what's the barometric pressure if you're 99 miles? Turn around, plug in 99 plus 1, you get 100 base 10. What I like to do here is another way to approach this problem is here's a little shortcut that you might see here. You see log base 10 result 100. What I like to do sometimes is I'll say base 10 raised to the what, and then remember that's what log 10 base 100 is. What is that exponent? You're told the answer, the result is 100. A lot of times when you write that out, you could see that 10 raised to the what is 100, and you're trying to find the exponent, and that would be 2. That's just a little shortcut if you like that. So you can replace log 10 base 10 result 100 with the exponent, which is 2, and once you've done that, that's the key thing they're trying to get you to see here on these problems. Now from here you're multiplying away 1.105 times 2 plus the 27, and you get your final answer 29.21. Okay class, we have wrapped up section 10.3 page 6. I'll catch you back here. We'll go ahead, we'll keep pushing forward here. We're going to move on to 10.4. We're going to do properties of logarithms when we get there. Okay, bye.